So the next reaction we're going to look at is very similar to halogenation, but what we're doing is we're forming what's called halohydrins. Halohydrins have this kind of functional group where we have a halogen and an OH, and that's essentially what we're going to be adding. It's the addition of a single halogen atom and OH across an alkene. And this occurs in an anti-fashion as well. So let's look at an example of this and kind of look at the similarities and differences between the last page. We're going to use, again, diatomic halogen as the source of the halide, but then we're going to use water as well. So it's bromine and water all mixed together. And when that occurs, bromine adds to one side and OH will end up adding to the other side in an anti-fashion. Now, because the stereochemistry is very similar to halogenation, the mechanism is going to look almost exactly the same. So the first step is the same. One of the bromines will make a bond to one side of the double bond. We'll use these pi electrons to make a bond with the bromine and kick off this one. So we get the same intermediate, this bromonium ion bridge. And we still end up with like half going up, half going down. I'm not going to show the mechanism for the down one. It's the same. But instead of having bromide attack attack the bridge, water is going to attack. So that's a little different, but what's the same is that it always attacks from the opposite side. So the Br ends up and the water ends up down. And now I'm just going to deprotonate because oxygen doesn't like being positively charged. And that gets me to the products. Now, if I had showed the rest of the mechanism for the down one, this one here, then that's how we would get the other enantiomer. But you'll notice in this situation, or in this reaction, I should say, I'm adding two different groups. Why did I add the bromine to one carbon, the OH to the other, and not the other way around? Well, it doesn't matter in this case. But let's look at an example where it does matter. And we're going to see that because we're adding two different groups, there is regiochemistry involved. So we're going to add bromine and water. First step is we'll use bromine will attack one side of the double bond. Pi electrons make a bond to that same bromine. And we get this bromonium ion bridge. Now I'm just going to draw it upwards, but the downwards ring is also formed. And now the water has a choice. It could attack this carbon or it could attack this carbon. Now I want you to pause the video, go back in your notes, go back to the oxymercuration reduction reaction and notice the similarities. And I want you to take a minute and try to predict which one the water would prefer to go after. So now that you've done that, hopefully you did, pause the video, go take a look. You hopefully predicted that this carbon has more positive character because it would, in theory, form a more stable carbocation. And this carbon has less positive character. So the water will attack the more substituted carbon of the bromonium ion. And again, I'm just showing one stereoisomer. This also happens if or when the bromonium ion bridge is going down. I'm just showing one, and then we'll deprotonate, and that gets us to this product here. And then we'd also get the opposite, or we'd also get the enantiomer. All right, why didn't I draw a wedge on the bromine? Because that carbon it ended up on is not chiral, so I don't care about stereochemistry. I don't even care about stereochemistry for this one. It's not chiral. So you don't have to show any dashes or wedges if it does not end up being chiral. So hopefully you're noticing similarities between this reaction, the one we talked about, halogenation, and even with oxymercuration, demercuration, and how all of these things are intertwining, and how we can use very similar explanations to talk about the mechanisms for the reactions.